Right, so we just saw the Ohm's law, and the Ohm's law gave me a new formula over here, V upon I. So R is equals to V upon I, resistance is equals to voltage upon current. So we just saw the Ohm's law and the experimental verification of Ohm's law. So that was quite simple. Now we see about the two kinds of resistances. One is ohmic resistance and other is non-ohmic resistance. Of course, it is quite simple to understand is ohmic resistance, यानी क्या, जो ohms law को follow करता है वो ohmic resistance, और जो ohms law को follow नहीं करता है वो non-ohmic resistance. So we have over here ohmic resistance. The conductors which obey the Ohm's law are called as ohmic resistors or linear resistance. Examples are all metallic conductors such as silver, aluminum, copper, iron, etc. Nichrome, copper sulfate solution with copper electrodes, and dilute sulfuric acid at constant temperature. So these all are ohmic resistances because they are going to follow the Ohm's law. So there, the graph which I draw over here, if I draw a VI graph over here, it is going to be like this. So the VI graph for the ohmic resistance is going to be like this. So for such a graph plotted by for the potential difference of V against current I is a straight line passing through the origin. Okay, you will find that it will always be passing through the origin as shown in the figure, and the resistance R is same irrespective of the value of V or I. So whether I is going to increase or Y is equals to increase, the value of R, that is the slope of this particular line, is going to remain the same. So that's why the ratio of VI is constant for all values of V and I. Non-ohmic resistance, the conductors which do not obey the Ohm's law are called as non-ohmic resistors or non-linear resistances. Examples are LED, solar cells, junction diode, transistor, filaments of a bulb, etc. For these conductors, the graph plotted on the potential difference V against I is not a straight line, but it is a curve. So in this case, it will be a curve like this. Okay, or it could be curve like this also. It's not necessary. It could be like this also. But basically, it will be a curve. Why it will be a curve? Because there with increase in the voltage or increase in the current. So we normally voltage increase, so increase in the current voltage, there is a sudden increase in the current. So the ratio of V and I is not going to remain constant in this case. So we find that is not a straight line. VI, the graph plotted of the potential difference V against current I is not a straight line, but it is a curve. 8.6 shows a VI graph in case of a junction diode. So in case of junction diode, it is going to be this way. For the ohmic resistors, it is necessary that the straight line on VI graph passes to the origin. But for a non-ohmic resistor, it is not necessary that the curve on VI graph must pass to the origin. So it is possible that in case of a non-ohmic resistance, it could be like this, that it could even go in this direction like this. From here, it will be ohmic. It could be ohmic later on, but initially it is not going to be ohmic. So this is most of the cases there will be some transistors and diodes. जहाँ पे क्या होता है, initially it does not allow the flow of current to take place, but as soon as the current increase, not allowing the potential difference to increase, but as soon as the current passes a particular value, then it suddenly starts conducting and it is going to the current keeps on increasing. So till a particular value there is no change. It is not allowing the current to pass through, but ऐसे ही जैसे ही वो current increase हो जाएगा, एक particular point पे आ जाएगा, उसके बाद में suddenly there is a resistance which will be given by the circuit. So that is why it's a non-ohmic resistance. So non-ohmic resistance can also not only be curved, but it can also pass through, not pass through the origin. So it could be something which is not passing through the origin. The resistance of non-ohmic resistors, that is V upon I, is different for different values of V or I. The resistance of the particular value of V or I is obtained by finding the slope of the tangent drawn to the corresponding point of the VI graph. So the value delta V upon delta I is called the dynamic resistance given in the value is different for the different values of V and I. So yeah, it will be we are going to take some small point away, like for example we are taking this point, तो ये point और ये point लेंगे, उसका tangent draw करेंगे, फिर ये point से we find out the delta v, and with this point and this point we find out delta I, and then we will be saying R is equals to delta v upon delta I. So this is the dynamic resistance which will be there for a particular position or location of that particular resistor. So ohmic resistors and non-ohmic resistors distinction. Ohmic resistor obeys the Ohm's law. VI graph is constant for all values of V or I. Non-ohmic does not obey the Ohm's law. VI is not same for all values V and I. Ohmic resistors, the graph of potential difference V versus current I is a straight line passing through the origin, whereas the graph of potential difference of V for current I is not a straight line, but it is a curve which may or may not pass through the origin. Ohmic resistance, the slope of the VI graph is same as at all points of V or I at a given temperature, whereas non-ohmic, the slope of V and I is different for different values of V and I even at the given temperature. Example, on metallic conductors such as silver, iron, copper, nichrome, electrolytes with suitable electrodes, etc. Whereas examples are junction diodes, LED, transistors, and filaments of a bulb, etc. Now let's see the factors affecting the resistance of the conductor. So that's an important part. We need to find out the factors which are affecting the resistance of the conductor. So let's see the factors. The resistance of conductor depends on the following four factors. The first one, so resistance, factors affecting resistance. So first one is the material. So material of the conductor, whether the material is a good conductor, whether it's a bad conductor, what is the resistivity of that thing, उसका resistivity ज़्यादा है या resistivity कम है. So depending upon what is the properties of the material, whether electrically it is able to conduct electricity or not able to conduct electricity, that will be depending on that will depend the resistance of the conductor. So that was we are taking as material of the conductor, and we will take that thing to be as rho. So we can say that the resistance is directly related to the rho, that is the resistivity of the material over here. So या तो रो को बाद में देखेंगे तो भी चलेगा, because anyway there is going to be a constant, so let's not take this thing. The second thing is the length of the conductor. So next is length of conductor. Now we can easily identify this, or we can easily compare the resistance with the traffic on road. It's very simple. If I'm talking about moving from just one place to just 100 meters away, तो obvious है कि अगर मुझे 100 meters जाना है और वही रास्ते पे मुझे 1 kilometer जाना है, तो what is the chances that how many obstruction will I get in 100 meters and how many obstruction will I get in 1 kilometer? Of course 1 kilometer में मेरे obstructions ज़्यादा रहेंगे. So time taken for me, or we can say that the number of obstructions or the resistance when I am going for a shorter distance will be less, and if I am going for a longer distance will automatically be more. So that's why we can see that resistance over here will be directly proportional to the length. More the length I need to travel, more will the resistance. Similarly, more the length of the wire or the conductor, more will be the resistance of the conductor. Okay, so the resistance of the conductor is directly proportional to the length of the wire. The second is the thickness of the wire. So third one over here is thickness of conductor. Again we can compare this thing with the road again. Thickness, road के अंदर thickness यानी क्या? Broad कितना है? Obviously अगर कोई चीज बहुत ब्रॉड और कोई रास्ता बहुत ब्रॉड है और कोई रास्ता बहुत छोटा है, तो छोटा रास्ता रहेगा तो ऑटोमेटिकली इट विल बी हैविंग टू मेनी ऑब्स्ट्रक्शंस, whereas if it is a bigger road then the obstructions will be quite less because you can move around from here and there, so the movement will be more easier. So that means the thicker the wire, the thicker the conductor, lesser will be the resistance. So thickness, or I can say area of cross section, okay, instead of thickness it is better to say the area of cross section. The bigger the area of cross section, the easier will be the flow of current. That means lesser the resistance. So we can see that thickness of the wire, or we can say resistance, is inversely proportional to the area of cross section. Okay, it is inversely proportional to the area of cross section, or that is the thickness of the conductor. And finally, the fourth point is the temperature of the conductor. So temperature, now we very well know that what happens when something is heated. When something is heated, जो चीज पहले सिर्फ इतना मूव हो रहा था वो अभी इतना मूव होगा, और अगर ये इधर से एक पर्टिकुलर इलेक्ट्रॉन को जाना है और ये पहले इतना मूव हो रहा था तो इसको डॉज करना इजी था, पर अगर वो इतना मूव कर रहा है तो ऑटोमेटिकली इसको बाईपास करना यानी उसको ओवरटेक करना डिफिकल्ट हो जाएगा और इसको पास करना डिफिकल्ट हो जाएगा. दैट मीन्स मोर द टेम्परेचर, more will be the movement of the particles and more will be the resistance provided by the particular conductor. So we can see that the temperature will be converted, more the temperature, we can see that more the temperature, more will be the resistance. More the temperature, more will be the resistance. But it is not direct, because if we are taking Ohm's law and all, we know the temperature we are going to keep it constant. So we are not considering it in this particular part. So let's see one by one. Dependence on material of conductor. Different material have different concentration of free electrons, and therefore the resistance of the conductor depends on its material. Metals such as iron, silver, copper, aluminum, lead, etc. have the concentration of the free electrons in the decreasing order, so that identical wires offer resistance in increasing order. So it is seen that silver, copper, aluminum, lead के अंदर क्या है, the number of free electrons is in the decreasing order, यानी lead के अंदर सबसे कम और silver में सबसे ज़्यादा. Accordingly, the resistance of silver is सबसे कम and lead में सबसे ज़्यादा. So that's why the resistance offered by silver is the least and the resistance offered by the lead is the most. The substance which has a larger concentration of electrons offer less resistance. Therefore, they are called as good conductors. So one which has got more number of free electrons will have lesser resistance, and accordingly they are called as good conductors of electricity. But the substances such as rubber, glass, wood, etc. have negligible concentration of free electrons, hence they offer very high resistance, so they are called as insulators of the electricity. The second is dependence on the conductor, length of the conductor. A long conductor, the number of collisions of the free electrons with the positive ions will be more as compared to the shorter ones. Therefore, a longer conductor offers more resistance. In fact, the resistance of the conductor is directly proportional to the length of the conductor. That is, resistance is proportional to L. If the length of the wire is same, radius is doubled, the resistance of the wire will get doubled. So, agar length of the wire of the same radius is doubled, so if I increase the length, resistance also increases. If I increase the length 3 times, resistance increases 3 times. Okay, considering that I am not changing the thickness of the wire, right? So that is the relationship, that the resistance of a conductor is directly proportional to the length of the conductor. More the length, more the resistance, lesser the length, lesser the resistance. Dependence on thickness of the conductor. In a thick conductor, electrons get a larger area of cross section to flow as compared to thin conductor. Therefore, the thick conductor offers a less resistance. So the collision which is possible is less because it is a wider area. So it could move around without any collisions easily. That's why we see that the thick conductors will offer less resistance. The resistance of the conductor is inversely proportional to the area of cross section A, normal to the direction of the flow of current. Therefore, radius is inversely proportional to 1 upon A. If the radius of the wire is same, length is doubled, or area of cross section becomes 4 times, the resistance becomes 1/4. If the radius is tripled, the area of cross section becomes 9 times. So the resistance become 1/9 and so on. So you see over here that the radius of the wire of the same wire is doubled, then the area of cross section becomes 4 times. So क्यों? क्योंकि ये see when this is the radius, so radius के बाद में हम क्या अगर हम लोग it is pi r square, right? But that's the main thing. It is pi r square. So it is 2 times, so it will become r square. That will be 4. And ऐसे 3 times किया, so it will be r square. It will be 9 times. So that's why if the length remains same, if the conductor is doubled, the resistance will be 4 times, 1/4. Okay. If the conductor is doubled, the resistance will be 1/4. And if the conductor is tripled, so okay, the thickness of the the radius is tripled, the cross section becomes 9 times, the resistance becomes 1/9 and so on. Okay, so that is the relationship over here, that agar resistance is inversely proportional to the cross section area. Now when we are talking about cross section area, we are talking about a circular part which will be pi r square. तो r square के कारण the whatever is the radius में हम लोग ने change करेंगे, वो r square times it is going to change over here. So it is initially it was pi r, but it becomes pi r 2r, it will be 4r square. So automatically the radius has become 1/4. And if it is 3 times, it will be 9 times. So it is 1/9. Okay. So change in the radius by double, the resistance becomes 1/4. By tripled, resistance becomes 1/9. Dependence on the temperature of the conductor. With the increase in the temperature of the conductor, the random motion of the electron increases. As a result, the number of collision of electrons with the positive ion increases. Hence, the resistance of the conductor increases with the increase in its temperature. So, as I told you that as the temperature increases, the random motion of the body of the particles are going to increase, which automatically increase the collisions and hence increase the resistance. Hence, the resistance of the conductor increases with the increase in temperature. The resistance of filament of a bulb is more when it is glowing, when it is at high temperature, as compared to that when it is not glowing, that is cold. So if you take a bulb and when you are drinking a bulb, so initially when the bulb was cold, the resistance of the bulb would have been less. But as soon as you start the bulb and it gets heated up, the resistance of the bulb keep on increasing. So the temperature of the bulb or the resistance of the bulb is going to increase when it is working, and it's going to be less when it is stopped or cold. VI graph of a conductor at 2 temperatures. So figure 8.7 shows 2 straight lines A and B of VI graph of the conductor at 2 different temperatures T1 and T2. So T1 is greater than T2 respectively. The straight line A is steeper than the line B because the resistance of conductor is more for high temperature T1 than at temperature T2. So that is just going to tell you that the slope जिसका जाता है उसका resistance जाता है, and it is also seen that जिसका slope जाता है उसका temperature भी जाता है. So T1 is greater than T2. Now we talk about specific resistance. So experimentally it is observed that the resistance of the wire is directly proportional to the length, and it is resistance of the wire is inversely proportional to the cross section area. So we know that this is nothing but proportional to 1 upon pi r square, because that is the area of cross section. So we get over here that the resistance is directly proportional to this and diagonal. So if we combine these two, what will happen? It will be R is proportional to L upon A. Now to remove the proportionality sign, we are going to take a constant, and according to that constant, the constant is taken it as rho L upon A, where rho is going to determine the value of the material, the type of the material it is, the resistivity of the material. So that's why rho is the resistivity of the material. So rho is equals to resistivity of material. Okay, so that is this can also be written as rho L upon pi r square. So that is also correct thing. So hence we see that rho is a constant which is characteristics of the material of the wire and is called as the specific resistance or resistivity of the material of the wire. It is different for different material. So from the above relationship we get the specific resistance rho is equals to R into A upon L. So if L is 1 and A is 1, then R is equals to rho. That means the resistance of a wire of unit length and unit cross-sectional area is the resistivity of that particular conductor. So the resistivity of a conductor is the resistance of a wire of unit length and unit cross-sectional area. So we see that specific resistance of material is the resistance of a wire of that material of unit length and unit cross-sectional area. So that is what is very important. In other words, the specific resistance of the material is the resistance between the opposite faces of the unit cube of that material. So that's okay. That is the cube of the material kar rahega, so it will be opposite ends. So opposite faces of the unit cube. So unit of specific resistance. So we can always find out the unit of the specific resistance. We know that this is in ohm. This is in meter square. This is in meter, so meter gets cancelled, so it is ohm meter. So ohm meter is the SI unit of resistivity. So we get rho is unit of R into unit of A upon unit of L. So ohm into meter square upon meter, it is ohm meter. Thus the unit of specific resistance is ohm meter. Okay, so this is about the specific resistance. Now the specific resistance is going to depend upon again two factors. So first is the specific resistance of a substance is a characteristic property. It is different for different substances. It is very low for metals and always approximate 10⁻⁻8 ohm meter. Low for semiconductors 10⁻⁵ ohm meter, and but very high for insulators 10⁻13 ohm meter. So metals ka always the resistivity will be very low. For semiconductors the resistivity will be somewhat higher than these metals and but less than the non-metals, and the non-conductors or they will always be, insulators will be always very high. The specific resistance depends upon its temperature. It increases with the increase in temperature of metal, but it decreases with the increase in temperature for the semiconductor. So it is in semiconductor, it's a completely different thing. That normally for metals, yeah, as the temperature increases, the resistivity keeps on increasing. But in case of semiconductors, if the temperature increases, the this resistivity decreases. So that is the important part about semiconductors. So that is what we see over here, that for resistivity, first point is the material, so that is not a problem at all, so that is just general. But for temperature, it is seen that in metals, increase of temperature increases resistivity, but in case of semiconductor, increase in temperature decreases the resistivity. Okay, that is about semiconductor. And for alloys like constant and magnet, it remains practically constant with no change in temperature. So if you are using anything, any kind of a resistive material, so if I want that the resistance should not change with if in a circuit I don't want the resistance to change with the change in temperature, then I will use the alloy like constant or magnet, which will remain, which will have the resistivity same with increase in the temperature also. So that is the important part. Now note, the specific resistance of a material of a conductor is constant at a given temperature and does not depend on the shape and size of the conductor. So when we are talking about the resistance, resistivity is something which is not going to depend upon the length or area of cross section or the shape or size of the resistor. Okay, it is going to be constant for that particular material itself. So अगर वो कॉन्स्टेंट का बना है तो उसका रेजिस्टेंस इतना रहेगा, वो अगर समझो आयन का बना है तो उसका रेजिस्टिविटी इतना रहेगा. सो वैल्यू ऑफ दिस रो इज गोइंग टू बी सम कांस्टेंट which will be dependent only on the type of the material we are using. It is not dependent on the shape and the size of that particular conductor. For equation, from equation 8.16 equation is this one. It is evident that if the given length wire is stretched such that the length gets doubled, then its area of cross section will get halved since the volume remains unchanged. Now the resistance will increase to 4 times of its previous value. So if I take this and kind of stretch this, so when I stretch this, what is going to happen? The length is going to increase, but at the same time, there is also going to be decrease in the cross-section area. So cross-section area भी decrease होगा, तो volume is going to remain the same. See, volume is not going to change. ये volume जो है वो तो same ही रहेगा. उसको मैं extend कर दूंगा, तो क्या होगा? Length जो है वो कम हुआ, but the area has still remained the same. The area of cross-section has got decreased. So increase in length is decrease the area of cross-section, right? Due to this, और वो भी उसके अंदर रेडियस का जो डिफरेंस होगा उसके स्क्वायर के कारण, if the length is going to be doubled, then the resistance is going to be decreased 4 times. So it is this way that when the resistance increases to 4 times of the previous value, since because of the increase in the length, then twice because of the decrease in the area of cross section. So area of cross section के अंदर we can see r square के कारण it is going to become like double, so it will be 4 times. So that's why we are going to when we see the numericals, we are just going to take this part also. So they will come to know exactly why exactly it is, so that अगर ये double किया तो 4 times क्यों होता है, तो we'll take that thing. So similarly, if the length of the length is increased to 3 times by stretching the wire, its resistance becomes 9 times of its previous value. On the other hand, if the wire is doubled on itself, its length is halved and the area of cross section is doubled, so the resistance becomes 1/4 of its previous value. But in each case, specific resistance is unchanged. So that's the important part, that the specific resistance is going to remain unchanged in all the conditions. जैसे resistivity है, उसका reciprocal will be conductivity. The reciprocal specific resistance is known as conductivity. It is represented by the symbol sigma. Thus, conductivity is given as sigma is equals to 1 upon rho or L upon R upon A. L upon RA. The SI unit will be 1 upon ohm meter, or ohm raised to minus 1 upon meter raised to minus 1, or it is Siemens raised to meter minus 1. Now we need to see the choice of the wire which I am going to use for different applications. So it is this way: the choice of the material of the wire depends on the purpose or for which the wire is to be used. So first is the wire used for electrical connections or for power transmission. Such wire should possesses the negligible resistance. So when it is to be transmitting the power from one point to another point, or for electrical connections, I don't want that the wire should take up power. Okay, it should not take away some amount of current, and so that's the reason the wire will always be used which will offer minimum resistance. So negligible resistance. Due to the low or negligible resistance of connecting wires, the current in the circuit remains unaffected and the loss of energy due to heating is prevented. Hence, they are made of materials such as copper or aluminum whose specific resistance is very small. Further, they are made thick so that the resistance become low. So note that though the specific resistance of silver is less than the copper and aluminum, but because of its high cost, silver is not used. So of course, if you use a silver wire, it will be much more efficient, but it is not possible to use silver because it's very costly. So that's why we use aluminum or copper for the power transmission wires. The second is the resistance wire or standard resistance. So when I'm going to make a resistance, so when I want a resistance, I don't want that the resistance should increase or decrease with the temperature. That's why I'll be using the alloy of constant or magnetic. So such wires are high resistance and their resistance must not change due to change in temperature. They are made from alloys such as manganese, constant, etc., for which the specific resistance is high and the effect of change in temperature on that resistance is negligible. So the choice of the wire for making a resistance will be constant or magnetic, the alloy of the alloys such as constant and magnetic. A fuse wire, it is made of an alloy of lead and tin because its melting point is low and its specific resistance is more than that of copper or aluminum. So the resistance of a short and a thin fuse wire is more than that of a connecting wire, it permits current up to its safe limit to pass through, but an excessive current melts it so that it blows off. Now, fuse wire is a wire which is going to be acting as a protective device. We are going to learn it later on in the household circuits, exactly the fuse. But उसका main purpose क्या है कि अगर high current उसमें से अगर pass हुआ, so of course this is a fuse wire, then if the high current is passing through it, then it should melt, so that the current would stop and it will break the circuit. For that, what is required? That the resistance of this, okay, should be greater, and it should have a low melting point. So when the resistance is greater, so the current passing through will be greater. तो वो current जो pass होगा वो heat करेगा इसको और इसको melt कर देगा. So that is the main reason regarding or main fundamental principle regarding a fuse wire. It is made up of alloy of lead and tin, which has got the specific resistance is more than copper and aluminum, and the resistance of short. So automatically it permits current up to a certain limit to pass through. After that, it will melt. The filament of electric bulb are made up of tungsten. Wire is used for because it is high melting point. So tungsten ka melting point is high, and you want that the current should flowing through such that it heats up and it can give us light. So that's why heat होने के बाद में वो fuse off नहीं होना चाहिए. That's the reason it should have high melting point, which is why it is used of tungsten. The heating appliances, like elements in the appliances such as the heater, toaster, oven, etc. A nichrome wire is used. So nichrome is again an alloy which is going to be used for, because the specific resistance of nichrome is high and the resistance increases with a great extent with the increase in the temperature. So as the temperature increases, the resistance also increases, and accordingly it will get heated up and it is able to do the work of heating, like heaters, the toasters and irons. वो सब में nichrome wire use होगा. The last is superconductors. Experimentally, it is observed that the resistance of some substances like lead, tin, etc. decrease tremendously with the decrease in temperature and become almost zero in low temperatures range nearing about absolute zero. Such substances are called as superconductors. Zero resistance of the superconductor means infinite conductivity. Once a current starts flowing in a superconductor, it persists even when there is no potential difference across it. Thus, a superconductor is a substance of zero resistance or infinite conductance at a very low temperature. So this is, of course, this is not a thing which is already being used. It is something which is like theoretically there, that lead and tin, when you are going to be at a very low temperature, and they are at very low temperature, they are going to have almost zero resistance. If the resistance is zero, then the conductance becomes infinite. So they will be able to allow the current to flow through even if the potential difference between the 2 points is negligible, or even if it is not there. So that's why it is going to be used in that way. So superconductors are substances with zero resistance and infinite conductance at very low temperature. Example: mercury at 4.2 Kelvin, lead below 7.25 Kelvin, and niobium below 9.2 Kelvin are superconductors. The superconductors are not in common use since it is very difficult to achieve such a low temperature. However, they can be very useful if it is possible to obtain them at room temperature. The size of the computer could then be reduced to a few centimeters, and the power lines, they could then be made of thin wire, single wire. So that would be the advantage. If in future, if we are able to use superconductors, then the size of so many devices will be just restricted to a very small size because of the use of such superconductors. So that was about the first part of the chapter. Now we are going to the numericals of this chapter in the next video. So that was about conductance and resistance and specific resistance. So now we see the numericals. I'll just add on the thing over here, that is the another formula what we use over here, and R is equals to rho L upon A. Okay.